This video will explain our algorithm that our team developed for the CS201 project. For this project, we are tasked to create a hashcode algorithm to put similar strings into the same basket. In our case, we are given 16 character strings that represent DNA sequences which consist of various combinations of the characters A, C, T, and G. This project uses an error threshold to determine if a DNA sequence can be put in the same basket. For instance, given these two DNA sequences, they are very similar and they only vary by 6 characters. And let's say if the error threshold is 6, these two DNA sequences can be put in the same basket. However, if I have a DNA sequence that varies by more than 6 characters, it'll have to be put in a separate basket. Our goal will be to develop a hashcode algorithm that maximizes the number of similar DNA sequences in each basket and minimize the number of dissimilar ones in each basket. Before we explain our algorithm, I'm going to introduce the murmur hash because we'll be using the murmur hash in our algorithm later. The murmur hash is a non-cryptographic hash function that is random yet uniform, and because it is non-cryptographic, it is definitely less secure and have weaker guarantees. Nonetheless, we felt that this wasn't too important in our context as we're hashing for the purpose of putting similar sequences together. We specifically chose the murmur hash as it has fair performance in comparison to MD5 and SHA-1 as seen in the figure.
Now on to our main algorithm. We chose to use SimHash that is a part of the larger family of locality-sensitive hashing algorithms, as it has been tested to have better efficiency than its counterparts, such as the MinHash algorithm. The big idea behind SimHash is as follows. First, we extract a set of features from the document and weight the features based on priority as well as frequency of occurrence. We then hash them using a standard hash and combine these hashes into a single array of bits called the SimHash fingerprint by calculating a bitwise average of them all. We do this by keeping a tally for every bit starting from 0 and add the features weight to the corresponding tally if the bit is 1, but subtract the features weight if the bit is 0. From the final tallies, we set the SimHash bit to 1 if the corresponding tally is greater than 0 and 0 otherwise. And the result will be the final fingerprint to be returned. Now for the implementation, we chose to take a substring from the original sequence as we found better results during our experiments, which will be covered in the next section. For the hashing algorithm, we chose to use a modified version of the murmur hash mentioned in the previous slides, which runs in O1 time and space complexity, and it is the hash32 function as shown in the code which hashes each character to a 32-bit integer. In addition to the original implementation, we also do a circular left shift of bits, and the amount shifted increases with index to take into account the order of the characters. We then convert each 32-bit hash to a binary representation and add 1 to the tally if the bit is 1 or subtract 1 from the tally if the bit is 0. We then convert each tally back to 1 or 0 depending on whether it is positive or negative, and that will be our final SimHash fingerprint. Finally, we convert the binary string back into an integer and return it. As our murmur hash implementation runs in O1 time and space complexity, our overall space and time complexities are just dependent on allocating a contiguous memory in terms of arrays and looping through the features for our subsequence of length 7. However, if the DNA sequence is longer, say 32 characters instead of 16, we would most probably increase the length of our substring accordingly to obtain better experimental results. Therefore, we believe the overall time and space complexities of our algorithm is linear to the input size. Thus, it will be ON.
Alright, so now I'll move on to talk about the analysis of our experiments. We were trying to experiment around to see what's the best subsequence that we could form so as to get the best quality indicator and total similarity score. So we play around with the start and end index of our sequence that we're going to use run through our algorithm, and we're not actually allowed to tweak the other functions, but we did this just for testing. We changed up the app file to kind of iterate through different possibilities. So we tried sequences from 9 to 16 or 1 to 5. Basically, we tried different subsequence lengths as well as different starting and end points. And what we did was for each of these sequences, we actually ran a number of tests. We ran like 100 tests for each of the sequences, and then we got the average of those. We average them out to see which starting index and ending index perform the best. And so after that, we wrote the results to a CSV file so we can view it easily. So first we tried to play around the different starting and ending index for error threshold 6. And what we found was that for error threshold 6, actually the best performing start index and end index was 9 to this is 0 index, so from the 10th character to the last character. And actually you could see this produce like the best average total similarity score, as well as the best quality indicator score. Yeah. So this weighted total score is actually just the product of these two. So that's why we decided to go with index 9 to 15. So we tried to also tweak the error thresholds. After we tried error threshold 6, we tried error threshold 5. And again, the same results hold that 9 to 16 show the most promising results, having the highest weighted total score. But we also found that once we shifted to error threshold 4 onwards, it kind of started to change actually. 9 to 16 kind of fell off, and we can see that 6 to 15 is actually the best. But since we're unable to modify the code, so there's no way we can tell what the error threshold is gonna be, the error threshold that is gonna be used. So we still decided to stick to 9 to 16 because we were under the assumption that that's the main error threshold that will be scored.
So here are some algos we tried but didn't end up selecting. So first we tried a modified BK tree, which is a tree-based data structure used to find near matches to a string query. So in our case, we built a BK tree of DNA substrings of length 3 to dynamically generate their intermediate codes, which is something similar to a hash, and then convert each 16-character DNA sequence to a string of these codes. So here's a resultant tree generated for 3 mers starting with the letter A, with the integers in blue representing their corresponding codes. So for the main hashcode method, we actually iterated through the 3 mers of a compressed DNA sequence and then converted them to a string of integers using the hash map that we had generated from the BK tree insertions prior to that. But then we decided that this algo was unsuitable ultimately because it didn't take into account that some 3 mers that were sorted into separate buckets by the algorithm could actually be considered similar according to the threshold, and the generated codes for each 3 mer were also determined by the insertion order of the nodes. So the performance of this algo would be very inconsistent. So we also tried a rolling hash, which is a hash function where the inputs hash in a window that moves through the input. The main crux of our method was to store the 4 letters and their corresponding integers preset by us into a hash map and running a polynomial function by converting each character in a DNA sequence to its integer and multiplying by 10 to the power of n, where n is its position in the sequence. So this algo produced decent results, yet it will compromise scalability since the longer the string sequence, the larger the hash code, and this may cause an integer overflow. Thank you for your kind attention.